Hi everyone, I am Xinyi from University of Pennsylvania. I will introduce our work Cowbird. Cowbird is a system which can free CPUs to compute by offloading the disaggregation of memory. This work is done by me and my collaborators Liangchen, Vincent, and Qizhen. Recently, there has been a lot of interest in memory disaggregation, which is a technique that can allow applications expand their memory capacity by leveraging remote memory resources. There are many different types of memory disaggregation. One particularly interesting type is this file memory architecture. Imagine there is an application running in the compute node. It can access its local memory and local compute resources. In the meantime, it can also access the remote memory. This gives the application an illusion that it has a large memory pool, and the application can achieve good throughput even when the working set gets larger than local memory. The critical component that makes this type of architecture work is this high-speed communication channel connecting the compute and the memory nodes. Today, most common approach is RDMA. RDMA is so attractive because it can bypass the kernel. In the case of one-sided RDMA, it can even bypass the CPU involvement in fetching remote memory. Which means compared with TCP, one big benefit of RDMA is that it can reduce the burden of local CPU. However, is RDMA good enough? Surprisingly, we found that there is still CPU overhead even in one-sided RDMA. We did a CPU time measurement for one-sided RDMA read request. We first need to post the work queue entry into the work queue and then pull the completion queue to check whether the task has been finished. We measure the CPU execution time for single post and poll. We can see that even single post or poll takes several hundred nanoseconds for CPU time. To see why this is the case, let's break it down into more details. We found that there are several subtasks, including locking, ringing the doorbell, etc. Each of them requires expensive instructions like spin lock or mfans to ensure the proper ordering of the queue. As a preview of our system, by offloading all of these, our system Cowbird can reduce CPU costs of RDMA and free these CPU cycles to applications. Since even calling the one-sided RDMA has overhead, why not free the CPUs on the compute node like a Cowbird? Based on this, the core idea of Cowbird is to offload the transfer of memory away from the compute node. The design goal is to convert remote memory access into local memory access. Then the remote memory access will be served asynchronously by the offload engine. The trade-off here is that the async stuff may introduce slightly more latency, but it brings the benefit of reducing CPU overhead and improving the throughput. The primary challenge in Cowbird design is the definition of an interface and a set of offloading protocols which are general enough for different kinds of offload engines. In memory disaggregation, there are mainly two components, the compute node and the memory node. In Cowbird, we added a third component called offload engine. Cowbird is a framework general to all kinds of offload engine, as long as the hardware can generate network packets and have basic computation power to process the packets. The hardware used as an offload engine can be a programmable switch, a SmartNIC, or a Spot CPU cores. Currently, we implement Cowbird with P4 and Spot, but it can also be implemented to other hardwares like FPGA or SmartNICs. From the application's view, every time it wants to access remote memory, it only needs to do local memory access to insert its request into a request buffer. After the request is finished, it can do another local memory access to read the response from the response buffer. From the offload engine's view, it will issue an RDMA read to read the application's request from the compute node buffer, then processes to get the information about the remote access request. Then it will issue RDMA read or write to access the buffer pool in remote memory. Finally, it will write back the response to the application's response buffer. As an application, how to interact with Cowbird? Just like simple read, write, and epoll, we provide a very simple interface to use. Due to the time constraints, I will focus on async read as the example during this talk. The application will first call async read to issue a remote read request. Then it will receive a request ID. Using this ID, it can call function poll to check whether the remote data has been fetched. We separate the data into actual data and metadata. Metadata contains all the information for remote memory access, and we only remain the necessary part to make the metadata size as small as possible. For read request, the request address is the remote memory address that it wants to read from, and the response address is a local address where the read data will be written. We create 3 local RDMA buffers to store the metadata and the actual data for read or write requests. When the async read is called, the metadata is inserted into request metadata buffer. When the request is completed by the offload engine, the actual data can be read from the response buffer. Now let us focus on the detail of offloading protocols. Phase 1 is the setup phase when RDMA connections are initialized. We register buffer regions and send the config information to the offload engine. In probing phase, the offload engine will keep sending RDMA reads to read the Cowbird request from application buffer. The step 1 is offload engine will generate RDMA read to read the tail pointer of the metadata buffer. Then in the second step, offload engine gets the RDMA read response and check whether there is update for the tail pointer. In the third step, if there is an update, which means there are new requests from the application, it will generate the RDMA read to read the real content in the request metadata buffer. Then in the fourth step, it will pass the metadata in the payload. So in the third and fourth phase, where we execute and complete for the read request, so the first step is that after we pass the metadata of application request, we know this is a read request. So the offload engine will fetch the request data from the memory pool. In the second step, we use RDMA packet recycle here. We convert the RDMA read response from step 1 into an RDMA write packet to write the data back to the compute node. Then in the third step, the RNIC will return RDMA ACK as the response of the previous RDMA packet in step 2. We also recycle it and convert it into RDMA write to update the tail pointers to the response buffer. In the evaluation section, we aim to address 2 key questions. Can Cowbird deliver its promise of freeing CPUs on compute node? With these saved CPU resources, what benefits do applications can experience? And we did all this evaluation based on our 2 implementations, Cowbird P4 and Cowbird Spot. We use an open source key-value store called Faster as our application. Records in Faster are stored in a hybrid log, which is a log partition across main memory and storage. When the main memory is insufficient, all the data will be appended to storage layer, which can be SSD or remote memory, or etc. We adapt Faster through iDevice, the interface for its larger than memory part of the log. Except for Cowbird, we have 3 baselines. The first is the default storage backend in Faster that uses a local SSD on the compute node. The second is the one-sided sync and async RDMA, where the storage layer is in the remote memory. The last one, where we put the storage layer in the compute local memory, represents the upper bound on disaggregated memory performance. We run Faster with YCSB benchmark, and we use communication ratio to represent the CPU cores in memory disaggregation. We can see from the result, Faster with synchronous one-sided RDMA can spend more than 80% of its time on communication tasks. This is because it needs to do a lot of busy polling. With asynchronous RDMA, it has much less CPU overhead compared with the synchronous one. However, our Cowbird can further reduce CPU costs and constantly spend less than 20% of CPU costs. We further measure the throughput of Faster with different baselines versus Cowbird. The white bar is the performance of local memory baseline, also the performance upper bound in this evaluation. Compared with local SSD, the results show that using remote memory can achieve significantly better performance. One thing to note here is that when the thread scale, Faster itself becomes the bottleneck. So the gap between the one-sided RDMA and the local memory will get smaller. However, we still see that Cowbird can achieve almost the same performance with the local memory. As a summary, Cowbird is a system that frees CPU cycles in memory disaggregation. Cowbird is general to many hardware settings, and it can provide close to local memory performance. Feel free to ask me anything.